Welcome back, children. Now we have to do exercise 16.2, that is based on events. So what's an event? Event is a subset of the sample space. There are different types of events. Simple event means an event which has only one outcome. Then compound event means events having more than one outcomes. Then mutually exclusive events. Two events E and F are said to be mutually exclusive if they are disjoint, or E intersection F is equal to null set. In terms of probability, we can say that P of E intersection F is equal to 0. That is mutually exclusive. Then exhaustive events, E1, E2, etc. En are said to be exhaustive. Then what is the condition? E1 union E2 union etc. union En is equal to the sample space. Okay. So the first question, an experiment involves rolling a pair of dice and recording the numbers that come up. Describe the following events. A be the event, the sum is greater than 8. B be the event, 2 occurs on either die, and C, the sum is at least 7 and a multiple of 3. Which pairs of these events are mutually exclusive? So for this experiment, what is the experiment? Rolling a pair of dice. So you can write the sample space. For rolling a pair of dice, not a single die, pair of dice, what is the sample space? S is equal to set of ordered pairs, 1, 1, 1, 2. Sample space means set of all possible outcomes. So maybe we get 1, 6. Then 2, 1, 2, 2, 2, 3, etc. 2, 6. 3, 1, 3, 2, etc. 3, 6. 4, 1, 4, 2, 4, 6. 5, 1, 5, 2, 5, 6. So the last row 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. So there are 36 outcomes. Okay, this is sample space. Now what is A? A means the sum is greater than 8. So we have to find the sum. For the first ordered pair, what is the sum? 1 plus 1 is equal to 2. Then 1 plus 2, 3, like that. So the minimum is 2. What is the maximum value? 6 plus 6 is 12. So sum is from, it ranges from 2 to 12. Now A means it is the event, the sum is greater than 8. So sum is greater than 8 means we have to consider 9, 10, 11 and 12. So in which all pairs we get the sum 9. So A be the set. It's an even means set. It's a subset of this sample space. So 9 means how we get, here the sum is the last outcome, sum is 7. So the first row we can't take. The second row 2 plus 6 is 8. So these two row we can take. So the next row 3 plus greater than 8. Here we have 3, 6. That sum is 9. So we can write 3, 6. Now in the fourth row 4, 1 is 5, 4, 2, 4, 3, 4, 4, 4, 5 we can write. 4, 5 and 4, 6. Sum is 9, here sum is 10. Now in the fifth row, 5, 1, 5, 2, 5, 3, 5, 4. 5, 5, okay, then 5, 6. Now in the last row, 6, 1 we can take, 6, 2, 6, 3 onwards. That is 6, 3, 6, 4, 6, 5 and 6, 6. So this is event A. Now B. What is B? 2 occurs on either die. That is either 2 is in the first place or in the second place or both. So that all pairs we have to write. So we can write 2, 1, 2, 2 we can write, 2, 3, 2, 4, 2, 5, 2, 6. Here 2 is in the first place and here 2, 2 means both the places. Now 2 in the second place, that is 1, 2 we can write, 2, 2 already there, then 3, 2, 4, 2, 5, 2 and 6, 2. So that is B. Now C. C means the sum is at least 7 and a multiple of 3. At least 7 means 7 or more. Sum is more than 7 and more than 7 and at the same time multiple of 3. So sum is multiple of 3 means we have to take the sum is 7 or more than that, isn't it? So 7, 8, 9, 10, 11, 12. These we can take, but multiple of 3 means only 9 and 12. So in which all pairs we get sum 9 and 12. So can you say C? How we write C? The sum 9. The sum 9 that we can write 3, 6. 9 is a multiple of 3. 6, 3 also we can write. Okay. Then 4, 5. Sum is 9. 5, 4. Okay. Then 12. How we get 12? That is for 6, 6. Only this case. Okay. So there are 5 outcomes. Now what is the question? Which pairs are mutually exclusive? Which pairs are? So you consider A and B, A and B, B and C, and A and C. 3 pairs we get. Which are mutually exclusive? Mutually exclusive means intersection null set. Check A and B. Is there any common element? So A intersection B is equal to null set. Therefore A and B are mutually exclusive. Are mutually exclusive. Now what about B and C? B and C also mutually exclusive. B intersection C is equal to null set. Therefore B and C are mutually exclusive. Now A and C. A and C, look, A and C, the first element is common to both. Okay, like that 6, 6, 6, 3, 4, 5, 5, 4. Okay, so C is a subset of A. So this A and C, they are not mutually exclusive. Okay, so which all pairs are mutually exclusive? A and B and B and C. The next one, 3 coins are tossed. Describe. There are 5 subdivisions. 2 events which are mutually exclusive, then 3 events which are mutually exclusive and exhaustive, 2 events which are not mutually exclusive, 2 events which are mutually exclusive but not exhaustive, and the last one, 3 events which are mutually exclusive but not exhaustive. So we have to describe from which is the random experiment. 3 coins are tossed. So take the sample space. From that we can take each one. What is the sample space? 3 coins are tossed. So brackets HHH, then HHT, HTH, write all the possible outcomes. There will be 8 outcomes. 1, 2, 3, 4. Now H and double T, THT, TTH and TTT. So these are the possible outcomes, 8 outcomes. Now the first one, look at the first one. 2 events, we have to describe the events. Okay, anyway you can define. So E1, one event, E2, another event. We need 2 events which are mutually exclusive. So from this you can take which are mutually exclusive. So here I am writing, let E1 be the event. Getting mutually exclusive means intersection must be null set. Okay. So getting at least two heads. Getting at least two heads means two or more heads, that is 3 head, here 2 head, 2 head, 2 head. So only this much, that is 4 outcomes in E1. Then E2, getting at least 2 tails. What do you mean by 2 tails? At least 2 tails, 2 or more. So here look this fifth case, 2 tails, 2 tails, 2 tails, and here 3 tails. Now what is their intersection? So this first 4 is in E1, the last 4 is in E2. So here E1 intersection E2 is equal to null set. So we can say that, where is the first one? They are mutually exclusive. So this is one particular example. You can write in another way. Okay. Not compulsory to write this one. You can describe in another way. Okay. Now the second one. What is the second one? 3 events which are mutually exclusive and exhaustive. Exclusive and exhaustive. Exclusive means, mutually exclusive means intersection null set. And exhaustive means their union must be the sample space. So in that way you have to define. So here we need 3 events, E1, E2 and E3. Okay. So E1, let E1 be the event, getting no heads. So what is E1? Getting no heads means TTT, isn't it? No heads in that. Now E2 means getting 1 head. So E2 means getting 1 head is HTT, THT, 1 head. Then getting at least 2 heads. At least 2 heads. At least 2 means 2 or more. So double HT, HTH, THH and sorry, it is HHH. Is it correct? 2 and more heads. Now compare this E1, E2, E3. What can we write? What is their union? E1 union E2 union E3. So all the elements you have to write. 1, 2, 3, 4, 5, 6, 7, 8 elements. And all these 8 elements are different. That 8 elements when we write, that is the sample space. Then what is E1 intersection E2? Is it null set? E2 intersection E3, null set, and E1 intersection E3, that is also null set. So what we can say here, E1, E2, E3 are mutually exclusive. They are pairwise disjoint and exhaustive. Okay. Now third one, 2 events which are not mutually exclusive. Not means the intersection is not null set. So define 2 events which are not mutually exclusive. So we can write getting at least 2 heads. At least 2 heads means 2 heads and 3 heads. Here I am writing getting at most 2 heads. What do you mean by at most? At most 2 heads means 2 heads, 1 head, 0 head. Okay. So they are mutually exclusive? No, they are not mutually exclusive. I'll write here. What is E1? E1 means 2 and more. That is double HT, HTH, then THH and triple head, that is even. Then E2 means at most 2 heads, that is HHT, HTH, THH. Now one head we have to write, that is HTT, THT, TTH, and what? 0 head. 0 head means TTT. Now you compare E1 and E2. Is the intersection null set? What is E1 intersection E2? The first 3 elements are common to both. So it is not equal to null set. Therefore, they are not mutually exclusive. Not mutually exclusive. Okay. Now fourth one, 2 events which are mutually exclusive but not exhaustive. 2 events which are mutually exclusive but not exhaustive. Look the third example, E1 and E2. They are not mutually exclusive. And the question is, they are not mutually exclusive at the same time but not exhaustive. What is the union of E1 and E2 here? In the third example, E1 union E2. E1 union E2 means HHT, HTH, THH, then triple H. Then here 1H and 3T. When we take their union, it is same as the sample space. So this example we can't write. You have to describe in another way. Write 2 events which are not mutually exclusive and at the same time not exhaustive. So we can write getting 3 heads and getting 3 tails. So what is E1? Triple H. E2 is, okay. Then E1 intersection E2, that is null set. And over here what we need? 2 events which are mutually exclusive. Okay. So intersection is equal to null set. Intersection equal to null set. Here the intersection is not null set also. Okay. Here intersection is null set. And what is their union? E1 union E2 is equal to, is it same as the sample space? No, only 2 elements. So it is not equal to S. Therefore, E1 and E2 are mutually exclusive but not exhaustive. Clear? Now one more in that is the last one, 3 events. We have to define 3 events which are mutually exclusive but not exhaustive. So 3 events you have to take which are mutually exclusive but not exhaustive. E1, E2, E3. So E1 be the event getting no heads, okay, as in the third subdivision, isn't it? Now E2 means getting 1 head, and E3 means getting 2 heads. So E1 means T, 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 and E2 1 head, HTT, THT, and TTH. E3 means 2 heads, HHT, HTH, and THH. Okay. So E1 intersection E2 null set, E2 intersection E3 is null set, and E1 intersection E3, that is also null set. Okay. Now what is their union? E1 union E2 union E3. Here how many elements? 3, 3, 6, 7. The one element that is missing is triplet, that is not in this union. So this is not equal to S. So what we conclude? E1, E2, E3 are mutually exclusive but not exhaustive. The next topic, axiomatic approach to probability. So this is another way to describe the probability of an event. So according to this approach, how to define the probability? So this S, capital S indicates sample space. So let S be the sample space of a random experiment. Then this P, capital P, is a real valued function whose domain is the power set of S. Domain is the power set of S, and range is the closed interval 0, 1. Okay. So it is a function. S means it is a sample space of a random experiment. Then the probability P, that is a real valued function. It is a function whose domain, for a function, domain and range. Domain means set of x values and range means set of y values. So domain means what? Domain is the power set of S. Power set means set of all subsets. So domain, the left hand side means it is the subset of this particular set, and the right side range. Range means it is a closed interval 0 to 1. So the probability of an event, the minimum is 0, the maximum is 1. It cannot be more than 1, it is not less than 0. Okay. Then, so this is the axiomatic approach. S be the sample space of a random experiment. P is a real valued function whose domain is the power set of S, and range is the closed interval 0, 1. Also satisfies some axioms. 3 axioms are there. The first axiom, for any event, E. The notation for event is E. For any event E, the probability of this event must be greater than or equal to 0. Okay, probability must be greater than or equal to 0. The second axiom is probability of the sample space is always equal to 1. Then the third axiom is, if E and F are mutually exclusive events, then mutually exclusive means intersection null set or probability equal to 0. So if E and F are mutually exclusive events, then P of E union F, P means probability of E union F is equal to P of E plus P of F. Okay, so these 3 axioms. So what are the axioms? For any event E, the probability of E must be greater than or equal to 0. For the sample space S, P of S is equal to 1. And if E and F are mutually exclusive events, P of E union F is equal to P of E plus P of F. For example, if we consider tossing a coin, the sample space S is equal to H comma T, only 2 outcomes. Let E1 be the event getting a head. Then E2 be another event getting a tail. Okay, so what is P of E1? Getting a head. Probability, how it is defined? Number of favorable outcomes by total outcomes. So H means only 1 out of 2. P of E2, tail, 1 tail out of 2. So is this events, probability of event greater than or equal to 0? Yes, P of E2 is also greater than or equal to 0. Then what is the sample space? HT. What is P of S? P of S means total, the 2 out of 2, that is it must be equal to 1. Okay. Now E1 and E2, are they mutually exclusive events? Yes. E1 intersection E2 is equal to null set. What is E1 union E2? H comma T. So what is P of E1 union E2? 2. Total is 2 out of P of S. In S, how many events? How many outcomes? 2. So P of E union E2 is 1. What is P of E1 plus P of E2? E1 is 1 by 2 plus 1 by 2. Half plus half is 1. So all the axioms satisfies. This assignment, that is we assign E1 probability to the event E1 as 1 by 2, probability to the event E2 as 1 by 2. So this assignment satisfies all the axioms. Okay. So just you have to remember which are axioms. The probability of an event is always greater than or equal to 0. Probability of the sample space is equal to 1. Okay. Then if E and F are mutually exclusive events, then P of E union F is equal to P of E plus P of F. So there is a question in the exercise, the first question. The question like this: does the assignment satisfy or it is the valid assignment? You have to check. So first you have to add all the probabilities. If it is 1, okay, and at the same time you have to check whether the probability is greater than or equal to 0. If the assigned probability is negative or total is more than 1 or less than 1, then that assignment is not valid. Okay. Now the next one, how to find the probability of an event? The number of favorable outcomes by total number of outcomes. Now how to calculate probability of A or B? That is P of A union B. How to calculate? In the axiom, if A and B are mutually exclusive, then P of A union B is P of A plus P of B. That is mutually exclusive case. Otherwise, how we calculate? So look at this Venn diagram. A and B. This blue shade indicates A intersection B. This part is A minus B and here B minus A. So from the figure, first I am writing A union B. A union B I can write as A union B minus A. Is it correct? And they are mutually exclusive. A means this first circle. B minus A is this red color portion. Okay. So these two sets are mutually exclusive. So using the axiom I can write P of A union B as P of A plus P of B minus A by the axiom. Okay. Then equation 1. Now I am taking B, the set B as, is B as A intersection B union B minus A? Is it correct? And they are mutually exclusive. This blue color portion and red color portion, they are mutually exclusive. So by using the axiom, P of B is equal to P of A intersection B plus P of B minus A. Equation 2. Then 1 minus 2. So P of A union B minus P of B is equal to, right hand side, P of A minus P of A intersection B. This term cancel. Okay. So what is P of A union B? P of A in the right side, take this B to the other side. So it is plus P of B minus P of A intersection. So this one you have to learn. P of, proof is not important, just this result. P of A union B is equal to P of A plus P of B minus P of A intersection B. As in the first chapter, N of A union B is N of A plus N of B minus N of A intersection B. That is number of elements. The same way, probability of A union B is probability of A plus probability of B minus probability of A intersection B. If A and B are mutually exclusive, then this last term becomes 0. So, P of A plus P of B. Now, probability of the event not A. Not A is denoted as A dash, as A complement. So, P of A complement is 1 minus P of A. Okay. Proof is like this. If A be the event, then A complement, its complement. So, other than all the elements in this A complement. So, their union must be is equal to S, sample space. Then what is P of A union A complement? That is P of S. P of S is 1. Okay. And A complement are mutually exclusive. So, we can write P of A plus P of A complement. So, what is P of A complement? 1 minus P of A. Okay. We have to learn only the result. Not A means P of A complement, that is equal to 1 minus P of A. Then A and B, what is the notation? A intersection B. So, probability of the event A and B means A intersection B. Now, how to denote not A, probability of the event not A and not B. So, P of not A is A dash, not B, B dash. So, in between intersection symbol. That is same as this, neither A nor B. That is P of A complement intersection B complement. Then how to find that? For that we use De Morgan's law, that is in the first chapter. Actually that is not in the syllabus, but you have to learn the result. A union B whole complement or A complement union B complement is equal to A intersection B whole complement. Okay, here we have P of A complement intersection B complement. So, the notation is, the bracket we can write as A union B the whole complement by De Morgan's law. Okay. So, A union B whole complement is same as A complement intersection B complement. These two are De Morgan's law. So, here we apply De Morgan's law. A complement intersection B complement is A union B whole complement. Then P of A complement, how to calculate that? P of A complement 1 minus P of A. So, 1 minus P of A union B. For A union B we have the result. So, we have to apply that. Okay. So, only that much about axiomatic approach to probability.